Good afternoon, good evening, good morning, wherever you are. Welcome to this plenary session. My name is Simon Redfern. I'm here in Singapore today, and it's my great pleasure to introduce Didier Queloz to you. Didier is, as you will know, a leading astronomer, astrophysicist in exoplanets, and he's going to be talking to us today about exoplanets and life in the universe. It's a topic of particular interest to me because I'm a geoscientist, and Earth scientists have always said that the Earth is our best data set. Well, of course, we didn't want to take on challenges like trying to find Earths around other stars, but this didn't deter Didier. More than a quarter of a century ago, during his PhD, he started developing spectroscopic methods to study the wobbling of stars in distant parts. In particular, he looked at a star in the constellation of Pegasus and noticed the oscillation of that star, which indicated the presence of the first observed exoplanet, the first planet outside of our solar system. And he's gone on to develop methods that have been used by the community globally to explore distant planets. And the interest of, I think, of these explorations of distant planets is what they tell us about our own origins, about the origins of life. And this is where Didier's research is now heading. And he leads up research groups in Cambridge and also in ETH Zurich to discover life beyond our planet and the origins of life. And I think that, Didier, is your topic for today. People want to hear from you and not from me. So I shall hand over to you, Didier. Thank you.
Thank you, Simon, for this very nice introduction. So I will share my screen. Hopefully this should be working. You should be seeing my first slide, right? If I don't hear anything, it means it's okay. Yeah, it looks okay. So I think it was clearly described by Simon just before that essentially we're moving from the perspective of looking at the Earth and using all these many planets we have found on other stars and trying to understand the origin of life. And that's a bit what I will try to convey to you, is to explain how we're going to do that. It's still something that we have not done, but there is a lot of elements that are piecing together right now, which is extremely exciting, and which is, I believe, the beginning of a new era, or certainly maybe possibly a new discipline, which is merging a little bit different other more established disciplines. So let's talk about exoplanets, so planet on other stars, and the connection about life in the universe. Well, the best start for that, and it's the solar system itself. The reason why is it is, and it will be for a very, very long time, the only planet that we will have the possibilities to study in great detail, to go there, to land there, and hopefully to bring back rocks or maybe gas and some of the other satellites of a giant planet back to Earth for being studied. So that is the starting point when we talk about planet on other stars, is to use our own planets as a reference. And well, I don't want to start the whole on what is our planet made, what is history, but there is something which is nice that you can understand very well if I open two different kind of giant planet, one which is called the gas giants. Jupiter is the best example. Saturn is about the same, and another giant which is called ice giants, which are Uranus and Neptune. And when you break apart and look at what is inside, what you see, what you understand is, well, of course, we don't break it apart. I mean, we just sense it with flyby and using the gravity. I think development of the gravity on the modes of the gravity that we sense this. There is a core, which is a solid core in the middle of the planet. And then there is a lot of gas. In the case of Jupiter, most of it is gas. It's the primordial gas, hydrogen, helium you find. In the case of Uranus and Neptune, there's a lot more heavy gas, but there's still gas, and also the core. And then we're left with the tiny planets like the Earth and Mars and all the telluric planets with essentially all this core material. Well, the fact you have a core is essential in the whole history of the formation of the planet, because it is the way the planet is being formed. They are collapsing on the core. This is called the core collapse, I think, mechanism, and they're collapsing. They're bringing by accretion the element together, and they accrete material from a seed, which is the beginning of the planet. This is the way the planet is being formed. It's by accreting the gas on the top of it when there are gas left over. When there is no gas, you have to glue all this solid element together. And that's the formation of the planet, which is very different from a star, which is collapsing the clouds of gas and making by the collapse the star at once. The planet is more like a slow build-up from the seed, assembling all the bits together. And from the solar system, we have a very good understanding of what a planet should be. And we have this global, let's say, mechanism that we used to, we used to understand from the fact that there is a lot of material when you are away from the sun, just because of the gas becomes solid material. This becomes just because of the change of phase. So you have a lot of material which is gluing together, and you can assemble the gas, which is solid in this case, and building up a core material much quicker, much faster for planet slightly remote, like Jupiter, for example, and Saturn. So the core is assembled from a lot of these solid particles made usually of gas, but because it's far away, it's solid. And then when you reach some mass, you start accreting all the other piece of gas, which you cannot reach a solid state, which is the hydrogen and helium, and then you bring up this big planet. And that's how we understand this big planet outside. And in the case of the telluric planet, you slowly glue together all the pieces you can find around, which is in that case more silicate based when you form the planet. And that is the understanding we have on the planetary system. So up to the point we had planet on other stars, everybody had in mind that kind of structure. And this is the reference structure that we all using as the reference of a solar system planet. Now, when we started looking at other stars and finding for the planet, we all had the system in mind, but frankly, we had a big surprise. We had a big surprise because most of the planet we have found, and I say we, it's the whole community, it has been now thousands of planets been detected. And from the day one, and we kept being surprised on the planet we have found. And to try to picture that in a very simple diagram, I have collected all the data that we have right now on the planet, on other stars, all the exoplanets, and I've collected only 3 parameters. I've collected the orbital period of this system in days. I got the radius of this planet. So we got the radius because some of these planets are transiting. So there is a brief moment when the planet goes in front of the stars. And from that, we can find out the size of the planet or the radius of the planet. Or we have some of the planet for which we get the mass because we see the motion of the star due to the planet. So we use the Newton law, essentially, and to get the mass of this planet. So this is a 3 parameter. It's a very, very fundamental and basic parameter that we have on the system. And it's already these 3 parameters are telling us a very fascinating story. Well, on the diagram, I divided the 2 because some planets, they do have a size and not a mass. Some, they do have a mass and not a size. I didn't want to mix it up. The blue is a planet for which has been found with the radius. The red is with the mass, and some of them have both. That's why you see red in the blue part and blue in the red part, because some of them have both the mass and the size directly measured. There is no model here. This is real data. This is the fact. This is nature, what it is. Now, I overlay on this diagram the solar system planet that I added Jupiter. Pay attention, the unit is in a mass of the Earth. here. So 300 times the mass of the Earth is Jupiter. And in size of the Earth, Earth radius, and about 10 times the Earth radius is the size of Jupiter. You have Jupiter and you have the Earth here and Venus here. The reason why I did that is just to just make sure we all understand that all the planets that we have detected, whatever we're using one technique or the other, are drastically different from the planet of the solar system. And if there is one element have to be remembered on more than 20 years of discovery, is a lot of the planet looks very different from the one we had in the solar system. And that's a bit of an embarrassing situation because, as I said at the beginning, the planet we know very much are the one of the solar system. So we have to extrapolate. We have to use the solar system planet and try to find out how far different they are. And to do that, we have to understand this data pretty well. First, we have to understand that there is a limit into the techniques we're using. The transit cannot find much planet with a period longer than a year, typically, because the likelihood of a transit is dropping dramatically, and even with space equipment like Kepler. This is why there is a limit, and anything on the right side of this diagram here, on this line that you see here, it cannot be seen. So that's the first element to understand. Well, no, there is also a detection limit. That is also telling you there is a limit in the size. If the planet is too small and the period is too long, you cannot find it. The mass is the same. There is also a limit. And when you look carefully at this limit, you realize for the transit, most of the solar system planet, actually all of them, they're outside this limit. So the transit cannot find any of these planets. In the mass measurements, which is using the Doppler techniques, we find Jupiter, and we have found Jupiter, but we're failing at finding Earth planets. So this is a bit of a situation. It's a fascinating situation because we cannot detect planet like the Earth, but we have found plenty of other. So what we have found is this blob of planet, this kind of, we don't call them population, but that's a group of planets called hot Jupiter. They are on short period. They have the size of Jupiter. They have about the mass of Jupiter. This is where the first one was found, and it's not just. I think it has to happen because they are the most easy to find. So you always start finding with the most easy. I used to mention during my PhD defense that it's likely to be the tip of the iceberg, and it actually is the tip of the iceberg because there is the whole population under it, that we call the super Earth and mini Neptune's planet, which are also on short period. Pay attention to this blob. There is a lot found in the transit techniques because the transit is very, very sensitive for that. Which are all this planet around this 10 days, 20 days, and size 1 to 2 to 3 Earth size. Similarly, in the mass, we have also the mass of this planet that we call the super Earth and mini Neptunes that have no counterpart in the solar system. And then we have some planet that seems to be like Jupiter, that have been found by the Doppler techniques. They're on the red dots on the right here, and they have the mass of Jupiter. But you may also see there is a lot of others, Jupiter kind of a planet, some of them which is 10 times more massive than Jupiter. And if you keep rising the mass, you reach a point when you become a star again. So you have to rise the mass up to 80 times the mass of Jupiter, and then it's just, you have enough pressure to make to ignite the thermonuclear reaction. And so you see, it's a very, very different picture, a very much complex picture than the vision we had before. Now, to make our life even more complicated, when you do the statistics of this kind of groups of planets, then you have a big shock, because you find out there's few percent of this hot Jupiter, very rare, 1 to 5%. 10 to 20% seems to be like Jupiter. Jupiter being seen in a very broad sense. It could be smaller, bigger. Some have very eccentric orbits, so don't see that on Jupiter exactly. But more than half of the star, up to 80% of the star you see in the sky that are kind of similar to the sun, they have planets which are fitting in this kind of blob of categories, which we call the super Earth and mini Neptunes on short period. So it seems that when you form a planet, the likelihood you will end up with a planet like the solar system is not common. We don't know if it's rare because we cannot compare right now. And we cannot compare because we have this dotted line here that tell us the techniques we have is not sensitive enough. And we're working quite hard right now to try to beat this. And that's the big challenge for the next 20 years, is to be able to detect this planet that are similar to the planet like the Earth, or we used to call them the Goldilocks planets or planet Earth twin, to be able to understand how rare we are. And no, the question is why our system is like it is and why this system is where they are. I think this is also a big challenge to understand the formation. So to understand this, we have to go one step deeper. We have to go to the nature of this planet. And to do that, we can combine these two parameters, the mass and the size, and to establish the bulk density of the planet. The bulk density is the first level of information about the astrophysical content of the planet. And in a way, it starts connecting to the planetary physics of the planet, to the first order, because the bulk information you're getting. When you do that, and we have quite a substantial number of this object, and there is more every day, because there is a couple of space missions right now, TESS and Cheops, which is deep digging into this, trying to find out as much object of that kind when we get the mass and the size at the same time. You have this very interesting and broad distributions of object. We have the hot Jupiter on the top with the size of the size and the mass of Jupiter. We do see that they are slightly bigger than you would expect. We call that inflated. And that's one of the reasons why they're inflated is because they have, well, the short period of this planet is such that they receive a high level of energy from the stars, and something like in the physics of the planet is affected and is changing the behavior of the structure of the planet. It's not only energy coming to the planet, because the planet is pretty much isolated as an entity. It's likely some physical mechanism that is related to the state equation of the planet, which is being modified by this. There is more electrons, free electron, there is more ion, there is certainly more element that is triggering this. People are still debating exactly how to do that, but that's a fact. Most of them are inflated. When you detect the planet a bit further away, they tend to shrink down onto this Jupiter and Saturn bulk density, which is the dotted line in gray you have here on the diagram, which is where you expect a giant planet to lie. So you can move the mass of the planet, remove the mass, the size will decrease according to this equation, which is a typical equation of state we have for that kind of planet. But what's interesting is when you reach the mass of Neptune, clearly the state equations of Jupiter and Saturn cannot explain the size of Neptune. Neptune is much more denser, and there is a good reason for that. There is far less hydrogen and helium, in ratio compared to Jupiter and Saturn. It's a much more denser planet. The gas are much more heavy because Uranus and Neptune have not changed, could not trap enough hydrogen in the formation process. And that's why it's sitting a bit below. And there is this blue dotted line, which is kind of a concept which is very hypothetical, which is what we call water planet. If you use the water, we know quite well the water equations for the phase transitions of the water is well understood, and for plenty of reasons is well studied for the Earth and under very high pressure as well. So we can use the water equations to predict if you make a planet entirely of water. Of course, the water inside will not be the same as the water outside, because the pressure, there will be a different phase, and there is a whole series of kind of water. I mean, if you want more detail on the water state equations, please have a look on Google. It's quite amazing how many water you can have. And you would be laying into this region, which is telling you this is a kind of a compact planet, which is made of a material which is very simple, that can be both gas and solid, depending on the nature where and the temperature of the object, which is kind of ranging a region where we used to fit the mini Neptune's area. And if you continue going down in size, even more denser for the same mass, and you understand, you can take a mass of 10 Earth mass. I mean, you take the 10 Earth mass, and you can move from the water world, when we have a lot of discoveries of planet of that kind. But you also find much more compact object, which is along this green dotted line here, and the green dotted line is where you would expect to have the Earth. So you see the one Earth mass, one Earth size. If you use the state equation of the Earth, assuming it's still valid, you keep going up, and you can bring mass and you increase the size, and you have also this planet here. So in this bulk of planet that I mentioned, which is what we call the compact super Earth and mini Neptune's object, actually there is a big mix. There is a mixing of objects which have the bulk density of the Earth, other that have clearly a much more extended atmosphere, likely closer to what's called water world. And even you can even have object, and you have some planet which has 10 mass of the Earth, which is much more higher on this diagram, which is completely inflated, which seems to be more likely to be closer to a giant planet and even more puffy than the giant planet, similarly to hot Jupiter. And we have kind of hot Jupiter even at that side. So it's a very, very interesting picture we're having, because we are extending the kind of class that we had with the telluric planet and giant planet and ice giant planets or systems to a much more diversities of planet that we need to understand. And the bulk density is just the first level approach. We need to do much better to understand what we're talking about here. So this is about where we are right now. We have this whole series of options of planets, depending if you have a big core, small core, a lot of gas, little gas, and a lot of solid particle and a little solid particle, and you see the diversity that we're having. At the end, you would only see a difference by playing with the mass and the size and the number of detail layer you want to add into the planet. So it's a very open questions right now, and one way to make progress is for some of these planets to detect the atmosphere. Some of these planets have very thick atmosphere, like the ocean planet, the gas dwarf, and the mini Neptunes, and this atmosphere can be detected. The Earth-like atmosphere are so tiny that they are clearly out of boundaries right now for astrophysicists. They will be in the future, but that's where we're making progress. We're going to make progress to find out what are these other planets by trying to look at what is in the atmosphere of the systems, and how can we do that? So I will just spend a bit of time, because this is really an active and actually very timely topic. The reason why is we're using this kind of transit configurations when we have the planet going in front and the back, and these two very specific moments when the planet is in front, called a transit, and a planet behind the stars, which is called an eclipse, I think can be captured by big telescopes. And sorry, I've been speaking too fast here. And we have all followed, I guess, a successful launch of James Webb Space Telescope. This is exactly where James Webb Space Telescope will be playing a key role, is detecting this specific event for exoplanet science. And more than 20%, 25% of the telescope time will be doing that kind of science. There will be a space missions called Ariel doing only that. And we have a series of big telescopes being built right now. One of them is the LT. There is others that have, as part of the bulk science, the purpose to study that. How does it work? Well, you look at the star and you look at the flux coming from the star, the light coming from the stars. If you do that, there's events that you will see that will change the amount of light you will receive. The first one is a transit. So here's a drop of flux at the time of the transit. And then there is a time when the planet is behind, called eclipse. Now, if you think a little bit about that, when the planet is behind, which is the eclipse, this is the only moment here. The only moment on the bottom is the zoom of the top. It's the only moment when you only see the star, right? Because the planet is behind. So because you only see the star, you have to imagine that the flux up to that level is the star. Anything above comes from the planet. So when you look in these configurations, if you have the sensitivity, and if you can find out where sit the star level, anything that is above comes from the planet and is the emission from the planet atmosphere. And that's how you can learn about the planet atmosphere. So that's one of the big techniques that people are using. We can use called the phase functions, which is the fact there is a dark side. The dark side is when you have the transit, you see the dark side of the planet. When you have just before the eclipse, you have the day side. And depending on the amount of flux, you have an idea of the temperature of each of these phases. And if you can do spectroscopy and have a very detailed analysis on the light curve, but not the light curve, through spectra, so you can even see line differences if you have a big telescopes. You can pick up wind of the planet and has been done already. We are picking up wind, and we can know what is the nature of the atmosphere in the dark side and in the day side from that. So, having a system like that, you can do much better than just the size and the mass. You can really get something from the atmosphere. The other very classical way to address the nature of the atmosphere is to use the transit itself. The reason is the transit is changing depending on the wavelength you're looking the object. The planet does not look the same in the infrared and in the visible. And the reason for that is because of the atmosphere of the planet doesn't have the same transparencies. You may be able to see through the atmosphere in some wavelength, or you may be blocked to see through that. To show you an example, I will show you what it looks like on the Earth. So let's imagine you have the Earth. This is the moon in that case, but let's assume the Earth is transiting the moon. So you see the very tiny atmosphere, which is the very challenge right now to detect from another planet, is 20 kilometers, which is a Rayleigh scattering. That's the reason why you see the blue sky. Well, if I use a wavelength, which is in the infrared, similarly to the military satellites, spying satellite, they see through this atmosphere. They don't see it. And at the very same moment, if I do the same picture, look exactly at the size of the atmosphere next to the moon. When I flip it right now to the infrared, you see the planet looks a bit smaller because we don't see the atmosphere anymore. So we see the planet itself. We see the surface of the planet right now because we're observing it 8 micron. It's a very different wavelength. Now, I can use the infrared as well, but to select a region that is sensitive to one very specific molecules that I know there are plenty in the atmosphere, very high in the atmosphere. We all know these molecules. It's ozone. So when you detect the ozone, when you look at the ozone, which is a very strong feature of absorption feature of 9.6 micron, the very same picture with the ozone band will look like that. So the planet is much bigger, of course, because then you are sitting 50 kilometers above the surface of the atmosphere. So I just show you that to give you an idea that we can measure molecular feature in the atmosphere of planet just by measuring the size of the planet. Of course, you need a total flux. You need to be able to go to the infrared. This is why we're going to space. This is why we're so excited about James Webb Space Telescopes, because this is something that will be done. We are going to do that. We're going to do that on the Neptune-like planet, on the super Earth, and we may be lucky, and we may detect very big atmosphere, 100 kilometers, 200 kilometers. They would be sensitive enough to be detected by these techniques. If the atmosphere is 10 kilometers, that would be challenging. But big atmosphere will be detectable on some of these planets that we have detected so far, because we know them right now. 20 years we're looking for that, so there's plenty right now around. And that's where we're going to make progress, because we will understand a bit better what is about the atmosphere of the planet. Now, when you talk about the atmosphere of planet, a lot of excitement comes about life. I mean, what does it mean for life? And then we have to be very clear. It's a very, very complex problem, and you cannot solve the problem in a very naive way. The first naive idea I want to kill, if you detect oxygen, it does not mean life. You can produce oxygen in the atmosphere of a planet in plenty of different ways, and that's a diagram I stole to Vicky Meadows that produce a lot of different ways. I mean, this is geophysics. When you interplay the physics of the planet, the physics of the atmosphere, and you can break apart water and you get oxygens. And you can even take oxygen from the CO and the CO2 and break it apart and making oxygen. So there's plenty of ways to make oxygen. So stop thinking that detecting oxygen is a sign of life. So how can we make progress on the origin of life? Well, we have to go back to the beginning in that case and try to find out what are the ingredients of life. What should we try to test to understand the possibility of life into a planet? And here you have to rely on modeling of life. And there has been, since a couple of years, a new development and progress being done on the origin of life that may be coming from the surface of the planet. The idea is very simple. When you bring a couple of simple ingredients together, like water, something from the volcanic activity, in that case SO2, SO3, and something coming from the infolding planet, that HCN, you have a neutral atmosphere, and you have a lot of energy coming from the sun, which is a UV flux. You're making chemistry. So the UV flux is breaking apart some of the molecule, making chemistry. And what has been shown is this chemistry is producing the 20 amino acids for which the life is being based on. That's a work that has been produced in 2015 by Patel et al. We tested some of these assumptions to see whether we have enough energy from the UV flux from the sun, whether it would work, and it does work, actually it does work practically on the solar system. So this is a realistic chemistry, at least to produce the amino acid. Of course, the amino acid is not the origin of life, but I just show you that, telling you that studying the atmosphere of a planet is telling you a bit of the story, because the atmosphere of the planet is something that will be a static element. This is something that will be evolving, and this is the connection with geophysics. Actually here, I think we know from the study of Earth that there has been a lot of evolution in the atmosphere of Earth, but the problem of the Earth is essentially we have no traces on the first billion years because of the plate tectonic has removed any useful information about the origin of life. So we're going to push that and to extend this concept into other planets. How does it work? Well, if you take the Earth as an example, again, because this is a good starting point, this is where we can at least say that there is life, at least one life that we understand, and try to make a story about this. So one of the famous diagram being used in geophysics is you divide the time of the evolution on Earth, and I like to use this diagram because it's connected many different disciplines. So you have to understand when you're talking about the planet, it's a very evolving environment. So from the early phase, which is called the nebular phase, when you make the planet, this is where the astrophysicists are detecting formation site, detecting protoplanetary disk. They're telling what is the infalling comet falling, what is the chemistry, what are the chemistry available when you fall a planet? Because that's the starting point. This is the building blocks. You cannot invent chemistry until you have the ingredients to make the chemistry on. Now, the planet, of course, will be a self-sustaining mechanism that will cool down and heavy material will sink. They will have a core. There will be a beginning of a magmatic activity. There will be a lot of infall impact, some of them dramatic, like the one creating the moon, and later on some maybe changing entirely the nature of the atmosphere. And the atmosphere clearly may have been enriched significantly by carbonate, for example, coming from the outside part, or water coming from the outside part of the solar system. It's a very likely scenario. So the atmosphere is evolving. So observing planet in its very early hot magmatic phase under the stars would be extremely useful as a comparison of what may happen on Earth. And then the planet cools down. You start somewhat the magnetic field activity, you start the volcanic activity, and you start producing some kind of prebiotic activities, or what I was mentioning. The atmosphere is full of CO2. This is what you get outside at the beginning, but slowly this is evolving, this is changing, and maybe at that point you start making life, and you start changing the nature of the atmosphere, or maybe not. Maybe you don't do that, and there's this whole concept of evolutions of the atmosphere, which is embedded into this book program. And a typical diagram is to study the amount of gas you have on Earth, and then of course for us astrophysicists, we're using that as template, because for each of the phases of the evolution of the planet, we can predict what is the emerging spectra, what are the molecules that we should be looking at. And these are the famous molecules we're very excited to look at, but not only on one planet, on hundreds of planets. We're trying to make a picture. It's going to take some time, clearly, 20 years, 50 years, but we're going to feel the diagram, and we're going to understand that planet has that atmosphere, that one has that atmosphere, and they may be related. Some of them will stay forever, like Archean Earth. Some will be having some kind of feature that is resembling to the Proterozoic Earth. And we'll have maybe a shark one day. We'll find an Earth twin. It's exactly the same kind of similar, or maybe not. We may never going to find that. Of course, embedded into that, you need formation scenario about the impact of this chemistry onto life. And you rely on lab work here to do that. And to assemble life is not only having the amino acids, you have to demonstrate that you're building them from small molecules to bigger chemical. How do you do that? How do you drive this process? What is the conditions? what are the mechanics of that? I mean, is it going to need river, lake, bottom of the oceans, rain, volcanic activity, all this putting together? You cannot address that until having a global model, because even the best chemistry lab is not resembling to the Earth. At the end, it has to be done in the dirt. So whatever you simulate has to be simulating the early conditions that you experience on the planet. So the planet is a lab. The life and the planet are intimately connected. They goes together. You cannot decouple the story of the planet from the story of life. And I want to mention, to end these discussions, what is going on right now on Mars. Mars is fascinating because Mars is essentially what used to be the Earth after 1 billion years old. And it's kind of frozen right now. It has not accepted the surface, but the rest should have been almost the same, not much differences. So we're very excited to studying this area, you know, the Jezero Cratera, which is really where we have a robot right now. There may be more in the future. And the reason why there is a lot of excitement about these regions is actually, if you go back in time, this region should have looked like something like that, like a big lake. So we are probing one of this idea that the origin of life may have happened related to flow of river and shallow lakes, with consequences into the chemistry. So what we expect for the Mars missions right now is to demonstrate that the assumption that it has been a lake and there has been interesting chemistry related to life is true. And that's the purpose of, probing this area and looking about the detailed chemistry that may be telling us of the early origin of life is what is going to happen when we're going to bring back some of the sample. Hopefully we will do very detailed chemistry analysis of these rocks as different regions, and hopefully we will find something that has disappeared from Earth, which is the origin of life, the early chemistry of life. I don't think we're going to find life, but we may have some tracer along the very complex molecules that is seen as essential through the process of making life. The fascination here is connects with sciences, and there is a lot of similarity between some of these sites on Mars and some you have on Earth, and some of them are famous to me, which is the Atacama Desert, where we have a lot of telescopes, and this is where all everything is connected together, because we have the Earth as a test case. We can predict using the Earth as a baseline what may have happened on other planets, and that's the most exciting diagram here, which is extracted from a report that has been produced by my colleagues producing the next generation of instruments after the James Webb Space Telescope mission. So we're already thinking much beyond, try to identify some specific event related to origin of life, comet impact, volcanoes, chemistry, impact of UV flux, with the chemistry related to that. What is the chemistry molecules? What is the signpost of life according to some of these events, depending on the wavelength? This is what is being done on the right side. And the idea is by collecting a lot of these molecules, observe on other planets, using the techniques I've shown before, and maybe later on direct imaging techniques, we will get gradually a better understanding on the origin of life on our own systems, whether we are alone or whether there are plenty of chemistry, but at some point life can start, but may not develop. And it's not obvious when starting life to me seems to be pretty easy because it's just chemistry going on. But whether you sustain it, you keep it growing, it's not given. This idea that as soon as you have a life, you keep it forever. I'm not very sure about that. So this is really the way to probe that. And it was mentioned in the introductions that we are assembling a kind of a global team on that. And recently we have been awarded funding to start a Leverhulme Center in Cambridge with a couple of partners in US, in UK, and Switzerland, trying to help making progress into that, acknowledging that we are not going to understand this program, which is very, very wide, very complex, without bringing three entities: the astrophysicist and the physicist, next to the chemist and biochemist, next to the geophysicist. We have to create a new community here, which will be able to understand all these many different elements together, trying to start developing a global scenario on the origin of life on Earth, and possibly, again, extrapolating. And the extrapolation is certainly the most difficult part of it. But as soon as we start collecting data, the extrapolation will not be completely in the wild. We will extrapolating between points, even if they are very remote. As soon as we start getting some data, we start globally assembling a global extrapolation. So it's a very, very ambitious program, and I'm pretty sure that we will accrete even more interest, and we will see this topic, flourishing and growing in many universities in the world, because it's so exciting, and that's kind of a new element that we can really address properly, combining this new development going on. So I would like to thank you and open some time for questions. Thank you very much.
Thank you, Didier. That was fantastic. Fantastic explanation. I certainly learned a lot about how you measure atmospheres. I'd always wondered how you measure an atmosphere of an exoplanet. So that was a fantastic tutorial. I really enjoyed that. Thank you.
Good.
And thank you for bringing us back to Earth at the end of it as well. Superb. I think I would completely echo your closing remarks on the excitement in this area. In geosciences, we often try and look back at these processes by looking at windows in time into the past in the Earth. You're looking at windows elsewhere in the universe, which is fantastic. Maybe I could ask a couple of my own questions that have occurred to me as you were talking. And the first was, one that's been in the news in the last week, the James Webb Telescope, and this fantastic unfurling of this instrument robotically. Fortunately, it all seems to have gone well. What's the time scale for us to start to obtain the sorts of data that you want? Your work is based on phenomenal observations and treatments of data that tell us new things. So how's that program going to unfurl in itself?
Well, I think James Webb is a gift. James Webb was designed not for exoplanet sciences, because at the time it was designed, there were no exoplanet. And in the course of the development and the growth of the topic of exoplanet, the James Webb has tried to realign a little bit the science to make sure they can observe also such a system. It was a big change. It does not happen very often in space development, because James Webb is designed to observe very faint objects in the beginning of the galaxies and the stars and the universe. And we are observing bright stars. So it's a completely different design, actually. But it has been done, and a lot of observation will go in the infrared with the James Webb. So we need to wait the James Webb to be cooled enough to observe the infrared region that we are interested about. The one I was mentioning, the ozone area, CO2 area, which is in the kind of 5 to 10 micron range. And there are programs, I know some people, I'm part of some of this program already, that have targeted exciting planet. One of the system is this famous system TRAPPIST-1, which we know there is possibilities that we have bigger atmosphere on some of them. So we're hoping that there will be detections. And it's planned. It's going to happen this summer and this autumn. And if everything goes according to plan, we may expect next year having the first results from James Webb Telescope. And since the launch was a great success, I heard that there is enough, consumable in the satellite that we may be able to operate for 20 years, which is great, because I expect to have more discoveries and more planets popping up in the meantime. So I think it's a fantastic mission, and we may be expecting to have surprise and good ones with the science of Webb. So it's a very exciting time.
It's always good to expect surprises. That's very good. Yeah. Another question I had about process and the way to do science, the way science is done. You early on in your presentation, you talked about the data sets of observations, and you refused to call them populations, but these distributions of observations and the limits of detection, which bias the data. Are there other problems? It struck me, how do you measure long period orbits when science is done on 3-year programs and 4-year PhD projects? And are those challenges, the way that humans operate, the human timescale?
Well, there is no challenges on the scientific side, because the scientists have understood that my work can be done because of the work of people in the past. Without Newton, I would not be doing what I'd be doing. So we all understand this timescale perspective. What is more difficult is to convince the funding agencies about this. And this is where we have to work, and we have to explain that when you do fundamental science called blue sky sciences, they have to understand that the time scale we're dealing with is of the order of 10 to 20 years. This is why we have tenure. This is why we have tenure positions, is to enable people not to be under stress for doing something. No, we have to be clever. When you build up a program on the long time scale, nothing prevents you to have some kind of milestone along the way when you produce some result which is of interest. And that's what we have been doing. So in a way, the science of exoplanet is so successful right now because we have been able to feed the community with results every month, and there is something going on. While we still have failed detecting a planet like the Earth, we have detected so many other interesting aspects. So as soon as you build up a new equipment, you have to be really open-minded and try to use your equipment for the best. So I'm not worried about this because everybody is aware of the time scale, but we should not be expecting the result at a specific time. It's difficult to plan it. We have to expect this uncertainty. I used to say, when Einstein started developing his equations of general gravitivity, who could have guessed this would be used for the GPS later on? Could you imagine Einstein writing the proposal? Oh, of course, later there will be an application. This is not how science works. So we have to accept that. We all understand that, but sometimes it's good to repeat it to the funding agencies.
Very good. There's some questions coming in from the audience, and one picking up on something you just said. Ian Nespekov asks, when someone discovers makes a new observation, a new planet, is there a kind of people flocking to this discovery to find out more about it? How does the science operate in terms of following up on discoveries and observations?
Well, I think there's a lot of follow-up because the field now has expanded. When we started, and the small club we were 25 years ago was only 50 people in the world. But now you must count 5,000 people working with that. So as soon as you produce a peer review and a result, there will be people looking at that. First, they will be looking at whether there is a flow into your data, as it has to be the case in science. They may wish to repeat the observation in some case when it's challenging. And they may want to come up with a new theory, and that's part of this kind of bubbling science activities. So yes, there are. Some of the discoveries are so big and they trigger a lot of interest, a lot of follow-up, and other are more immune for some time. And then 5 years later, we realize there is something fantastic on that object, and everybody revisit something that was seen to be boring at that time. And this is part of the science diversity. And what I love in my business is every day when I open my computer, I should be ready for surprise of the big news. So people ask me, when do you expect a big discovery? I say, can come tomorrow.
Yep, very good. And hopefully from some of the people listening today in good time. Yes. Yep. Another question that kind of, I think probably a number of us had in mind from Glenn Liu about life on other planets. Do you think life on other planets would be similar to that on Earth, in particular in terms of, I guess, the building blocks of life, amino acids, or are we biased by this one observation that we have?
Well, I think the chemistry in the universe is the same everywhere. So if you would assume that there is a minimum of chemistry, you should not be too much exotic, because the more common you are, the more likely it's going to repeat itself. So I do believe the very basic building blocks has to be everywhere the same, because the chemistry is everywhere the same, almost the same. The question is then, amino acid doesn't make life. And then what is the other ingredient that you need to pop up, and whether you may start life and then stop being alive because something happened. So do you need a series of timing events, like when you build a planet, that is really at the right time, and altogether that may be rare? And that's the big question actually we're asking. And frankly, my position is, you can argue whatever. The only thing that matters is whether you can bring data, or whether if you have a theory, you can test it. So a theory without test is irrelevant. And if you don't have the data, it's irrelevant. So my point is, we are at the stage right now where we're bringing a lot of data, either from the lab, from Mars, another planet of the solar system, and from exoplanet together. You can assemble theory, and you can make prediction and test it. And that's completely new. And this is why I think using the very practical techniques of the science, we're going to make serious progress for the first time ever. Because before that time, I think we have made zero progress on the origin of life, for good reason, because we had nothing to help us to understand this.
So a lot of your work has developed from new spectroscopic observations and new technologies that have developed it. And one of the questions from Cordelia Brown is about further developments in characterization. Are there things on the horizon that haven't been addressed yet? Other sorts of physical properties of exoplanets, for example, magnetic properties. Can we see aurora? Can we pick up other characteristics that in geophysics we are familiar with studying in the solar system?
Yeah, I think the magnetic activity is a very good point. I think we would love knowing about the magnetic activity on planets. There are some ways to learn something through the radio detections. I mean, we have been detecting the radio from Jupiter, and there is some possibility in the future, especially with the SKA, to have some element about magnetic interactions between particles from the stars and magnetic activity on the planet. But they will be restricted to a close-by planet. I think it will be difficult, and some of these elements will be almost impossible to get some detail on. Like, we will never be able to take some piece of the planet and bring it back. That which I think we should forget. But still, we can live with that, and we try to be a bit creative and find some side effects, like the rotation of a planet. I mean, one day we will make picture of these planets. It's just a matter of size of the telescope that you have in space, and nothing prevents us to build a big telescope in space. It's just the cost and the practicalities, but we can do that certainly in terms of possibility. There's no law of physics you break here. So by doing this way, we will be able to find out if there is some pattern, and then you will see the rotation of the planet. So maybe there is some element related to the activity, magnetic activity, you can pick. So, the creativity of the researcher is, it depends only on the limit you put to yourself. And I think there is a lot of possibilities, and you have to also acknowledge the technology is changing. So in my case, the reason why we have been so successful, because we benefit from two technology that became available, this fast computer and optical fibers. And that was a big change, building up a complete new generation of spectrograph. I know they all essentially build the same way. There has not been a real revolution on that. But maybe tomorrow there will be something new that will completely change the way we build some equipment. And the telescope already have completely changed the design of the telescope on the fact we can control the mirror at a very high level. And the James Webb Space Telescope unfolding and controlling each of the mirror is the result of this robotic progresses made in the last 30 years on controlling hardware, very precise. So there's a lot of technology that we're trying to use to build the most extravagant equipment you can think about it.
That's fantastic. Thank you so much, Didier. I think we would all love to hear more and learn more, and we look forward to learning more in the future. Thank you so much today for giving us your time and sharing your excitement on these discoveries. I think we've all enjoyed it very much. I certainly have. Thank you, Didier. Thank you, Didier.
Have a good day, good evening, and good morning, depending where you are.
Yep. Thank you. Bye-bye.
Bye.